Hey, this is Mr. Piercy, and this is going to be a video that I'm going to make for how you work the Pythagorean theorem with right triangles. The Pythagorean theorem is kind of the introduction to things that you would do with right triangles as far as uh, leading you into things to do with trigonometry with right triangles and even trigonometry with other types of triangles that are not right. This is one of the most famous theorems in mathematics. Everybody kind of knows what the Pythagorean theorem is. It's one of those things that you can just you learn it. It has that quality of being easy to roll off the tongue, almost like y equals mx plus b. So we have a squared plus b squared equals c squared is what we're going to be looking at with our Pythagorean theorem. So here, what it's used to find the missing sides of a right triangle. Usually sides A and B, the two sides that make up the right angle, those are called the legs. And side C, no matter what it is, the side across from the right angle, that is called the hypotenuse. Now, a lot of times, personally, I like to think of the side A as whatever the shorter leg is, and side B is whatever the longer leg is, but that's completely arbitrary. I could have called this side here B and this side here A, but the hypotenuse, the side opposite of the right angle, that's always going to be side C, the hypotenuse. And for any right triangle, we have a squared plus b squared is equal to c squared. So here what we have are just some examples to see, okay, well, what are we gonna, get when we work these out? Can you actually do these? And the arithmetic mostly should be, you still need to show your work on paper, but a lot of this, the calculations you can use with a calculator if you would like. So I'm going to work out a couple of these problems for you as an example, and then I'm going to ask you guys to try to work some out on your own just to make sure that you understand them. But don't worry, the work will still be given to you, presented to you. So for instance here, this is what I would look at as side A, and this is what I would look at as side B, and of course the hypotenuse is always the side opposite of the right triangle, or the right angle, I should say. So let me zoom in a little bit here so it's a little easier to see. So according to the Pythagorean theorem, we're at a squared plus b squared to be equal to c squared. So we just plug in those numbers. 8 squared plus 13 squared equals c squared, which we don't know. And again, if you don't know what certain numbers squared are, then jump on your calculator and see what you get. But here we have 64 plus 169 to be equal to c squared. And 64 and 169 give me a total of 233 for the length of the hypotenuse squared. Now at this point what we do is we're not interested in what c is or what c squared is. We're interested in the what c is, because right now c squared, that would kind of represent like an area of a square where all sides had a length of c on it. Okay, so what we do at this point is we take the square root of both sides to undo the c squared expression on the right side. Now normally what we would do is we would try to simplify this as a radical, but if you try to take the square root of 233, it doesn't really simplify because it doesn't have any factors that are perfect squares or anything. So in this case we would say 233 is equal to the length of c, or the square root of 233. And that as an approximate number, because the instructions do say round to the nearest tenth, Now for us, because we're training to be in an AP class at some point, we won't go to the nearest tenth, we'll go to the nearest thousandth. Meaning 3 decimal places. So this would be approximately 15.264 for the length of the third side. So I'm going to go ahead and move on to what I'd like you guys to do now is I want you guys to try doing example 2 because example 2 and example 1 are basically the same type of question. So go ahead and try working out example 2 and see what you get. And when you're ready, hit play and check your work with mine. Okay, so here's my work for problem number 2. Hopefully you were able to come up with these same solutions as I did for the length of the hypotenuse on example 2. The square root of 1213 would have been the exact answer, and 34.828 would have been the approximate answer. So now let's take a look at example number 3 and 4. So I'll do 3 and I'll ask you guys to do 4 just to see how you're coming along with it. And in this case, now we're not being asked to find the hypotenuse. Now if you notice, we're given the hypotenuse and we have to find one of the legs. So here we would say we'd still start it off a squared plus b squared equals c squared. And you could rearrange the equation if you want to. You could say that if I solve for a squared, since that's the side that I'm looking for, I can say that a squared is going to be equal to c squared minus b squared. So let's look at it like this. So a squared is going to be equal to c squared, which would be 9 squared minus 7 squared. So a squared is equal to 81 minus 49, and that will give me a squared to be equal to, what is 81 minus 49? 32. So now when I take the square root of both sides, this is going to give me a number where I could actually simplify it as a radical. So a as an exact number would be equal to 4 square roots of 2, or a is approximately equal to, so let me type it on my calculator here because I don't actually know the number, about 5.657. 5.657. So here, these are going to be the types of solutions that we would be expecting you to provide. A exact answer left in radical form or a rounded approximate answer, depending on the instructions that you're given. So same thing, I want you to go ahead and pause the video and try and work out example number 4 and see what you wind up getting for the length of the missing side. And when you're done, go ahead and hit play. So how did we do on this one here? So what I'm doing on example 4 is I'm still looking at the short leg as being side A and the long leg as being side B, where the hypotenuse is always going to be side Z. So according to the Pythagorean Theorem, a squared plus b squared equals c squared, I can rearrange that by subtracting c squared on both sides to say that b squared is equal to c squared minus a squared. And then I just substitute the numbers, 30.5 for the hypotenuse, 19.1 for the leg, square both sides, take the difference of them, and I get this 565.44 value, and take the square root of both sides. Now here, because of the decimal number underneath the radical symbol, clearly this one wouldn't simplify to be a simpler radical the way square root of 32 became 4 radical 2. But this would be what we would look at as the exact answer, and about 23.779 is our final value. Now the exact or the approximated values are nice because it gives us an idea of what it should look like. Based on the diagram, we can conclude that the hypotenuse always has to be the longest side because it's the opposite of the biggest angle. So that means this side here is shorter than this side, so that means my answer really should be between those two values, and that's kind of what we're seeing. Same thing back here on example 3. Here, this is the shortest side, so this side here should be smaller than either of these two numbers. So if you wind up getting something larger than 7 or even larger than 9, that should be an indication that you made a mistake somewhere and need to go back and take a look at the problem. So let's take a look here at the next two examples and see what we get. I'm going to do 5 for you, and then I'm going to ask you guys to do 6 and 7 on your own as practice, just to see how you do with them. So here, this one is, they're showing you that we have an isosceles triangle with the congruency mark showing that, this side is 24, so this side is 24. And essentially what we're being asked to do is to identify what's the altitude of the isosceles triangle. Well, one of the things that we know about an isosceles triangle is the altitude actually bisects the base. So since the base is 22 units long, I know that this side here is 11 and this side here is 11. So in this case, I would look at this part of the triangle, meaning I'm just kind of looking at, 1/2 of the isosceles triangle here. I would look at that as side A, the altitude is side B, and of course the leg of the isosceles triangle is actually the hypotenuse of this little right triangle that we're creating from it. So in this case, we're being asked to find b squared. So again, according to the Pythagorean theorem, I can rewrite it just like I did in the last example to say that b squared will be equal to c squared minus a squared. And now I can start substituting my values and see what I end up with. So here, c squared will be 24, and a squared will be 11. And now we just see what we wind up getting. So 24 squared gives me a value of 576. 11 squared will give me a value of 121. So 576 minus 121 is going to be 455. And if I take the square root of 455, that one doesn't really have any perfect square values to it, so it won't simplify. But we can take the square root of both sides. And in this case, I would say b is equal to, as an exact number, the square root of 455. Or as an approximate value, we would get 21.331. Okay, so at this point, go ahead and try working out examples 6 and 7. See if you can think your way through those problems, and when you're done, hit play and check your work with mine. Okay, so how did you do on 6? I decided that I'll go ahead and work 7 out with you. If you've already worked it out, then fantastic, but I have a feeling that a lot of people are going to get tricked up on number 7. So looking at number 6 here, because they're showing us that we have right angles here and here, that lets us know that this segment and this segment are parallel to each other because the sum of the same side interior angles is 180 degrees. So we can drop another perpendicular segment here to show that the corresponding angles are going to be the same. So here I know that this triangle that I'm making with this portion of the top horizontal segment, the diagonal here, and this dotted perpendicular line is where my right triangle is going to be. And here the length of this side of the right triangle is going to be the difference of the 18 here and the 5 here, because essentially we're just kind of bringing this vertical segment 5 spaces this way so we can actually make a right triangle. So this side of the triangle is going to be 13. The hypotenuse is going to be 16, plugging them into the Pythagorean theorem, where the short leg is equal to a squared, or a squared is equal to c squared minus b squared. We get 256 minus 169 when we square both sides, which gives us the square root of 87 that we take the square root of. 87 doesn't simplify as a radical, so square root of 87 is the exact value, and 9.327 is the approximated value. Now, taking a look at number 7, the reason why I think a lot of people are going to get tricked up on number 7 is that it's going to be very tempting for people to want to take the 14 here and the 29 here and do the Pythagorean theorem to find this length of x. Unfortunately, if you notice right here, the right angle symbol is missing. So this one is not a right triangle. And that's going to be the assumption that a lot of people are going to make, is that it looks like a right triangle. We're doing the Pythagorean theorem, so I mean, why wouldn't it be a right triangle? Well, unfortunately, it's not. The only we do know that we have a couple of right triangles in the diagram, however. Here, this triangle between this 14 segment and this 12 segment, that will be perpendicular here, or I'm sorry, a right angle here, because we have a linear pair, and if this one is 90, then this one has to be 90 according to, for what we understand about linear pairs. So I can do the Pythagorean theorem to find this side here, which I'll call A, and so let's go ahead and do that. So in this case, this would be the hypotenuse, and this would be the long leg. So again, I want to find the short leg here, so I'm going to say a squared would be equal to c squared minus b squared. So a squared is equal to 14 squared minus 12 squared. And I don't know what 14 squared is off the top of my head. 196 minus 144. So I get 52, and that one should simplify to be 2 square roots of 13, or you can say that A is approximately equal to, what would that be as a decimal number? Oops, I hit something wrong on my calculator. About 2.685. 2.685. Now, here's going to be something that we want to do, is because this length x is going to be the sum of this bit here and the sum of this bit here. So what I want to do is, whenever I add those, I want to use the exact numbers, not a rounded decimal number. Now, you could take the rounded decimal number and save it in your calculator and use that if you would like, but be careful about doing that. Make sure if you do any arithmetic with approximated values, make sure you save the decimal numbers in your calculator somewhere. So now we're going to find the length of this piece here. So now, looking at this kind of medium-sized triangle with the 12 and the 29, this side would be A, this side would be B, and this side would be C. The way I like to do it, I always kind of like to make the short leg A. So again, here I'm going to say A squared is equal to C squared minus B squared. And we're going to just run it through the process one more time here. So in this case, I'm going to say 29 squared minus 12 squared. And 29 squared gives me 841. 12 squared again is 144. So the difference of those is going to be the square root of 697. Oops, didn't mean to write the square root symbol yet, just 697. Then we take the square root of both sides, and the square root of 697 doesn't simplify. So this other side would be approximately equal to, what would that be as a decimal number? 5.138. 5.138, and that doesn't sound right. Nope, I think I typed something on my calculator wrong. So let's see, 697, that would be 26.401. I typed something wrong on my calculator here. 26.401. Did I make the same mistake on my calculator here? Let's see, what was the square root of 52? I did. I made something I typed on my calculator wrong. 2 square root of 13 is the correct number, but I wrote the wrong decimal number here. Okay, so here A is approximately equal to 7.211. So 7.211. Okay, so those are the two values that we have. So I apologize for the mistake here. 2 seemed a little bit small, but I didn't think about it at the time. I must have just typed something wrong on my calculator when I did the square roots. I don't know what I did, but so x in this case, what we're actually trying to find is the length of this bit here and this bit here, and I just realized I labeled this B and I labeled this A, so all of these should be a B. Okay, so here x in this case is equal to the length of that side A that I had in green and the length of side B that I had in gray. So here I could say that x is equal to 2 radical 13 plus radical 697. And that was what I would look at as my exact answer, but if I wanted to know what those actually were, I would just go to the calculator. 2 radical 13 plus radical 697 as a decimal number is going to be 33.612. So x is approximately equal to 33.612. So here, these are what we would look at as our two solutions for the length of side, this side here that they're calling x. If you do the Pythagorean theorem, if you just assume this is a right triangle, because again, the right angle is missing, so we don't know that this triangle here, the overall big triangle, we can't conclude it's a right triangle. If you do the Pythagorean theorem with 14 and 29, you're going to get a number slightly less than this. I want to say it's about 32 and change, but that is generally speaking how we look at right triangles. So now let's move on in the stuff that we're looking at with right triangles, and we're going to try and do some application questions. So at this point here, there's two more just general triangle questions that I want you to try and work out. Go ahead and pause your video, try working out problems 8 and 9, and then we will move on to the word problems with the Pythagorean theorem. So here are the last two examples. Hopefully your work and my work are kind of in sync with each other, but problem number 8 is the only really tricky thing about problem number 8 is you need to make sure that the value that you get for the missing side in between the two triangles, that you either make sure that you use the exact number that you got doing your calculations, or the decimal number that you get, you save it in your calculator. But this one is a two-step problem. We're looking to find the length of side x here, And we know it's a right triangle, so we have the hypotenuse of the right triangle, but we don't know this leg. However, we do have another right triangle here where I know the leg and the hypotenuse, so I can use the Pythagorean theorem with this leg and this hypotenuse to find this missing side here, which is 5 square roots of 21 units long. And then I can use that number in my second calculation where I say the hypotenuse 28 squared minus 5 radical 21 squared, and that works out to be the square root of 259, or approximately 16.093. So here, the last problem, number 9. This is a very classic type of setup in dealing with any type of right triangle situation, where because we understand that this side and this side we have perpendicular segments between them, that they're parallel, so this would be a trapezoid. In fact, it would be an isosceles trapezoid. So when we drop in these perpendicular lines here, the distance between them is going to be 26. And since we know the overall length of the base is 40, the difference between the 26 and the 40 is split between these two remaining pieces on the sides here. So that's how I'm getting 7 and 7. And so now we have the length of a leg and a hypotenuse that we can use to find the length of the height of the trapezoid here, which is the leg of the right triangle that we're seeing. And when we work it out, 20 squared minus 7 squared gives me 400 minus 49, which is the square 351. The square root of 351 does simplify as a radical, so we can leave 3 radical 39 as our exact answer, or rounded to 3 decimal places, 18.735. So hopefully we're getting a good handle on what we're doing with the Pythagorean theorem. The Pythagorean theorem is the basis of what we do for the distance formula that we've been using in geometry for quite some time. But now let's take a look at some word problems here. So let's take a look at 10 and 11. So here, a roofer leaned a 16-foot ladder against a house. If the base of the ladder is 5 feet away from the house, how high up the house does the ladder reach? So these are pretty typical type of problems. So maybe you got your like your house here, right, where this is going up towards that way, and we have a ladder leaning up against it. Well, the ladder is 16 feet long, so that is going to form the basis of our hypotenuse for the right triangle. And we're presuming that the side of the house is perpendicular to the ground, so that's where we're getting the right triangle from. And it says that the base of the ladder is 5 feet from the house. So the base of the ladder would be the part that's on the ground. So 5 feet here. And we're being asked to find out how far up the side of the house does it go. So we can call this side X, or height, or whatever you want to call it. So now that we have a diagram that shows us what our picture, or what our triangle is going to look like, we have our hypotenuse and a leg, so we're looking for another leg here. So I'm going to say the leg squared will be equal to the hypotenuse squared minus the other leg squared. And I want to say 16 squared is 256, but I don't want to guess here. Yeah, that's 256 minus 25. So that would be 231. And so the square root of 231, I don't believe simplifies. So I would say x is equal to the square root of 231, or approximately equal to 15.199 feet. 15.199 feet. So pretty close to the 16. So let's see. Yeah, pretty close to the overall length of the 16 feet of the triangle, or of the ladder. And I should put feet here, because they gave us a unit of measurement. We need to include it in our answer. And so the next one that I'll look with you guys is an example. Number 11, Kurt is building a rectangular deck. If the dimensions of the deck are 10 feet by 23 feet, what is the length of the diagonal of the deck? So again, a pretty classic type of problem using a non-right triangle figure to work with something with a right triangle. So because it is a rectangle, we know that all four sides are the opposite sides are going to be the same, and all four corners are going to be 90 degrees. And so what it's asking us to do is to identify the length of the diagonal. So they're telling us that one side is 10, that one side is 23. So in this case, the diagonal, I guess we'll call that D for diagonal. That not D for distance. Usually we use a capital D for distance, but I guess this is the same idea really. We're looking for the hypotenuse, so the diagonal squared is going to be equal to 10 squared plus 23 squared. And 23 squared is 529. So the diagonal squared is 629. And if I take the square root of 629, that does not simplify, so the diagonal would be equal to the square root of 629 feet, or approximately. And in these application type questions, the decimal values are really going to be the stuff that makes sense. We typically, aren't going to look at things as a length of a square root of 629. Instead, we really think of it as a length of, in this case, 25.080. So 25.080 feet. So the last two word problems, I want you to try and take a look at these on your own and see what you get for your answer. And when you're done, hit play and check your work and see how it compares to mine. Alright guys, so here are the last two problems. Hopefully your work and my work are going to match. The diagrams themselves don't need to be drawn in any particular order. Well, I guess with this one here, because we are going east and then we're going south, so east and south are perpendicular directions to each other, so that's how we know we have a right triangle. 3.4 miles one way, 5.7 miles the other way. So the length that we're looking for, the distance that she is from home, is going to be this diagonal here. So that works out to be 44.05 miles, or about 6.637 miles. Here, a 31-foot wire is attached to the top of a 25-foot pole. How far is it from the ground? Or how far is the base of the wire and the pole? How far is it when it meets the ground? Now here, realistically, this is a wire. It's not going to be perpendicular. Realistically, it's going to sag because of gravity. But we'll we'll just presume it's going to be a nice segment here for the purposes of the problem. So here the 31 feet represents the hypotenuse, the length of the pole represents one of the legs, and this side here represents the second leg. So plugging that stuff into the Pythagorean theorem, we get a distance from the base of the pole to be about 4 radical 21 feet, or 18.330 feet as a decimal value. And that is going to wrap up the examples that we have for how we are looking at the Pythagorean Theorem. So if you have any questions about any of these, be sure to get in touch with me. And until next time, guys, thanks for watching. Take care and be good.